So hello guys, today we are going to solve a little good question that goes by the name of power of 2. Power of 2. So this is question number 231. So it's an easy question. It's an easy question, but we will see whether it is easy or not. Okay. It code can write anything, but whether it is easy or not, that will be determined by your strength, by your question, the number of questions you have practiced. Okay. So let us first start by reading the problem statement. What does the problem statement say is, given an integer n, return true if it is a power of 2, otherwise return false. Okay, so it is just a simple question. It says like you are given an integer n and return true if it is a power of 2, otherwise return false. Basically, what they are saying is, if the n that you are given like 16, 17, it can be 17, 18, 19, or any number. If it is a power of 2, what does it mean by power of 2? Like it comes as 2, 4, 6, 8, 10, sorry, 2, 4, 8, 16, 32, 128, 64, 256. So if these are the powers of 2, these are the powers of 2 and expanded to any number. Okay. So if the integer n is a power of 2, then we have to return true, else we have to return false. Okay. An integer n is a power of 2 if there exists an integer x such that n is equal to 2 raised to power x. So if anything is 2 raised to power x, and that becomes the number, that becomes the n that we are given. This we are given, and this is ambiguous. This is not decided. This is not decided. This can be any power. This can be any power. Okay. So if something to the raised to power of 2 gives us n, if something to the raised to power 2 gives us n, so the number is said to be a power of 2. The number is said to be a power of 2. Okay. So I have explained you the question. So now we will see how we can approach this question. Seems to be easy, right? Seems to be easy. But is it easy? Okay. So first I'll tell you, before solving this, I'll tell you a concept. What the concept is? Bit manipulation. Bit manipulation. But what is bit manipulation? As the word says, something like, if you break it down into two words, if you break it down, one is bit and one is manipulation. But what are bits? What are bits? As we know that every data that is stored in our computer, stored in our PC, consists of bits or bytes. Bits or bytes. So bits is the smallest unit. Bits is the smallest unit of data. Bit is the smallest unit of data. And every data that is in your PC, something that contains bits. Basically, it is not shown as bits. It is basically shown in MB. But if we break down an MB, so it is eventually some kind of bits only, right? Like 8 bits are composing 1 byte. Okay, 8 bits compose 1 byte. So this was about what is bit. Okay. So now we have gone halfway through. Okay. What is a bit? We have understood. Now what is manipulation? Any type of manipulation. Manipulation means like changing or forming operations on the bits value, on the bits, is particularly known as bit manipulation. Okay. First, suppose I told you that every data consists of bits. Every data consists of bits. Okay, and a number like 1, 2, 3, 4, 5, 6, and so on. they are also composed of bits. They are also composed of bits. Okay. So these numbers can also be represented. These numbers can also be represented in bits. So I could easily convert these numbers to bits. Okay. Suppose one is written as 0001, two is written as 0010, three is written as 0011, four is written as 0100. But how I am writing this? How I am writing this? I don't know. Find it out yourself. No, no, I'm going to teach. Wait. Okay. So if I say that if we have to write the number 5 in bits, I have to find this bit representation. So how can I do that? How can I do that? Okay. So the bits, as you know, that the two computer understands only 0 and 1. Understands only 0 and 1. Okay. So for every digit, for every place, there are only two options. There are only two options, that is 0 or 1. 0 or 1. Okay. So this is also known as binary format. This is also known as binary format, that we are writing our numbers as a combination of bits. Okay, as a combination of bits. So how can I convert these numbers to bits? Suppose I have the number 5. I'll simply divide it by 2. I'll simply divide it by 2. Okay. And what I get as the remainder. If I divide 5 by 2, I get 2 because it is 2.5, but the floor of the value is taken. So it would be 2. And what is the remainder? Remainder in this case would be 1. Remainder in this case would be 1. This was the first step. Second step, I'll take the divisor, I'll take the quotient value, sorry, I'll take the quotient and put it onto the next step. I'll put it onto the next step. I'll put it here and I'll again divide it by 2. I'll again divide it by 2. So what I get is 1. What I get is 1. Is 2 exactly divisible by 2? Yes. So the remainder would be 1. Here I would be storing all the remainders. These are my questions. Okay. And this is what I am dividing. So I'll repeat the same step. I'll just put this one onto the, make it as a dividend. Make it as a dividend. I'll again divide it by 2. If I divide 1 by 2, it becomes 0.5 and floor of the value is taken. So answer is 0. My question becomes 0. And what is my remainder in this case? What is my remainder in this case? It is 1. It is 1. Okay. So what I have to do is for getting my representation, I have to take it in this order. I have to take all the remainders in reverse order. In reverse order. Like we came from 1 to 3rd, but my answer would be from in this order. My answer would be in this order. Why? Because every time we are basically dividing our value, we are going on to the left hand side. Suppose every time we are dividing our value, we are going on to the left hand side. Okay, because we are basically trimming down our value. From 5 it became 2 and from 2 it became 1. So we are pushing the values from the last. So this one would occupy the last position. This one would occupy the last position. This second position would be occupied by 0 and this third position will be occupied by 1. So this is what becomes my binary representation of 5. Of 5. Okay. If I tell you a number like 8, how is it binary representation gonna look like? Okay, so 8 I'll first divide by 2. This is my first step. This is my first step. I'll do it in 8 divided by 2. I'll write the dividend and divisor here, quotient here, and remainder here. Okay, so 8 divided by 2 gives me a quotient of 4. And what is the remainder? 0. Second, I'll take this value, I'll take this quotient and put it as a dividend. I'll put it as a dividend. So 4 comes here and it is divided by 2. So my quotient becomes 2 and my remainder becomes 0. Okay, I'll again perform the same steps. My quotient will be the dividend. So my 2 will come here. It is divided by 2. I'll get it as 1. And what I get it is remainder 0. Yes. And if I perform the same step, I'll make my quotient as my dividend. I'll divide it by 2. I'll get 0. And I'll get the remainder as 1. Okay, I'll get a remainder as 1 because we are basically dividing a smaller element by a bigger element. Okay, so so okay, so what I said it, we are filling our positions from the last index. So I'll push this onto the last element. I'll push the second one onto the second last, third one onto the third last, and the fourth one onto the fourth last. Okay, on the fourth position. Okay, so if I can observe something here is in both the cases, for 5, for 5, there are more than one. There are more than one in the binary, more than one ones in the binary representation of 5. Like 101 is the binary representation. It contains more than one 5. More than one ones means like it consists of more than one ones. Okay, like this one and this one. Okay, but if it is a perfect number, okay, if it is a perfect number like this, like 8, I'll tell you what a perfect number is. So if it is a number like 8, it can say consists of only one. It consists of only one once. Okay. So this is how you get the binary representation of a number. Binary representation of a number. Okay. Binary representation of a number. Suppose, suppose now I'll go back to the question, and what it says is we have to just return true if it is a power of 2, otherwise false. Okay, so I'll try to use this bit manipulation technique in this question. Okay, so so what I'll try to do is, if first tell me what are the powers of 2, what can be the powers of 2. Okay, so 2 raised to power n, suppose basically n ranges from 0 to any number. What can be my range? This is my domain, and what can be my range? Okay, so my range can be 0, maybe 0, 0, no, no, starts with 1, because 2 raised to power 0 becomes 1. Okay, okay, so 2 raised to power 1 becomes 1, then 2, then 2 raised to power 2 4, then 8, 16, and so on. Okay, and so on. Okay, so I'll just pick up any number. And I'll see what are the dissimilarities between these numbers and the normal numbers. What can I do? Suppose in this case, like we saw, like if it is a power of 2, because as every bit, like if I try to represent 8, okay, so 8 divided by 2, 4, remainder 0, 4 divided by 2 goes to 2 and remainder 0, 2 divided by 2 goes to 1, remainder 0, 1 divided by 2 goes to 0, remainder 1. Okay, so it has a binary representation of 1 0 0 0, 1 0 0 0. Okay, also, I want to tell you that the first digit is shown, the first digit can also be shown as 2 raised to power 0. It represents 2 raised to power 0. Second number represents 2 raised to power 1. Third number represents 2 raised to power 2. Fourth number represents 2 raised to power 3. 2 raised to power 3. So I just traverse from the right hand side, and I'll just traverse from the right hand side, and I'll see that the first digit is occupied by 2 raised to power 0, then 2 raised to power 1, then 2 raised to power 2, and the last digit would be occupied by 2 raised to power 3. Okay, 2 raised to power 3. Okay. If I try that for 8, it was 1 0 0 0. Okay, what is gonna be for 9? As it is 2 raised to power 0, that is 1. This is 2 raised to power 1, 2. This is 2 raised to power 3, 8. This is 2 raised to power 4, 16. Okay, 2 raised to power 2, sorry, 8, 4, and this is 2 raised to power 3 is equal to 8. So if this digit is representing my 8, I can write it as 8 plus 1 equal to 9. So I have to add a 1. I have to add a 1. What I will do is, for adding 1, I'll simply make this bit as 1. Make the first bit as 1. Because it becomes now 2 raised to power 0, and this is now 2 raised to power 3. So I'll just simply add both of these. 2 raised to power 3 plus 2 raised to power 0 is equal to 9. Okay. Okay. So what can be my solution? What can be my solution? My brute force solution can be, if we observe carefully, like not brute force, but there are some follow-ups that are given that you have to follow. Okay, follow along. So if you carefully observe, then all the digits in the binary number are represented by some 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. Is it something like same as what we got here, like what I shown you here, that the range of 2 raised to power ns, because 1 can be represented as 2 raised to power 0, 2 as 2 raised to power 1, 4 as 2 raised to power 2, 16 as 2 raised to power 4, 8 as 2 raised to power 3. So is this looking same? Is this looking little same? Yes. Okay. So if every digit is representing some value of 2 raised to power something, 2 raised to power something. Okay. If it is representing this, then if any of the digit is turned to 1, any one of the digit is turned to 1, I can simply say that, and all of the other ones are zeros, then I can simply say that this is my power of 2, this is my power of 2, because for the final answer what we are doing is, we're just basically adding all the values, because we are basically adding all the values. We are multiplying 0 into 2 raised to power 0, 0 into 2 raised to power 1, 0 into 2 raised to power 2, 0 into 2 raised to power 3, and 0 into 2 raised to power 4. So if all the other digits are 0, all the other digits are 0, and only one digit is 1, so only one element would be considered, only one number would be considered, that is 2 raised to power 2. If only this is considered, only one number is considered, then my power of 2 will then the number would definitely be a power of 2. Then the number would definitely be a power of 2, because if I try to say this, then 7 is represented by 0 triple 1, 0 triple 1. It has three ones. It has three ones. That means that 1 into 2 raised to power 0, 1 into 2 raised to power 1, 1 into 2 raised to power 2, and 0 into 2 raised to power 3. I'll just add them, and what I get is 0 into 2 raised to power 3 plus 1 into 2 raised to power 2 plus 1 into 2 raised to power 1 plus 1 into 2 raised to power 0. So 1 into 4 plus 1 into 2 plus 1. What it becomes is 4 plus 2 plus 1 is equal to 7. Okay. So I am multiplying the 2 raised to power with the current digit value. Like if it is 0, I'll multiply it with 0, and if it is 1, I'll multiply it with 1 and add all of them. Suppose I say that all the values except just one value is 0. So my overall the answer would contain only one value, that is 2 raised to power something. Okay, 2 raised to power maybe 4, 5 something. Okay, and all the other values are 0. So this becomes null. This all becomes null. So this is the only one that is 2 raised to power something. Okay, 2 raised to power something. So it is a power of 2. It becomes a power of 2. Because if everything else becomes 0, then there is only one digit, and that is 2 raised to power something, 2 raised to power 4, 5, or any number it can become. Okay, so this can be a power of 2. This can be a power of 2. Okay, so what can be my solution is, if you know this. Okay, what can be my solution is, if I know that 8 is 2 raised to power 3. Okay, 8 is 2 raised to power 3. How I can represent 8 is 8 divided by 2, 4 remainder 0, 4 divided by 2, 2 remainder 0, 2 divided by 2 remainder divisor quotient 1 remainder 0, 1 divided by 2 quotient 0 remainder 1. It can be represented as 1 0 0 0. Okay, now now you have got this value. One way to solve this problem is, you can just simply extract each of these values and put it into a string, and you will just traverse the string. When you just traverse the string, and if you find that there is only one, that is only one, only the digit 1 is present only one time. Okay, so then that number is a power of 2, because we just discussed that if all the other digits are 0, then my final answer would contain only a 2 raised to power x. This x can be any number. Okay, I'll just move it to a string, and I'll traverse the string to check if it contains only one like value of 1. Okay, understood, right? Only one once. Okay, and how can you extract this last value? I'll just AND it with 1. I'll just use bitwise AND for this value. Okay, so what this bitwise AND is, if you have ever heard about the table logical table, or what we call as the truth table of AND. How is it truth table of AND formed? Suppose we have two inputs, and this is the output. Okay, and we can have only two combinations. We can have only like two numbers, 0 and 1. So using 0 and 1, how many number of combinations can be made? 0 1, 1 0, 0 0, and 1 1. So we'll write it here: 0 0, 1 0, 0 1, and 1 1. So these will be the number of combinations. Okay, and in logical AND, what we do is, If there is one, if there are both ones, if there are both ones, then only we do this one. Then only the output is one. Okay. Suppose if there are two people in the team, suppose there are two people in the team, okay, and one means the person is working hard, and zero means the person is not working hard. Okay, and output is the project that you made. Okay, so if both the people will work hard, if both the people will work hard, then only the project can be made. If even one doesn't work hard, then the project cannot be made. If one doesn't work hard, project cannot be made. If both doesn't work hard, project cannot be made. So this would be true only in the case where one and one, both the inputs are fully given. Both the people give their full contribution. Okay, then only the output will one work. Okay, this was about logical and. Okay, what we do in bitwise and is bitwise and that is denoted by this bitwise and. Okay, so if suppose you have two digits 8 and 7, 8 is represented as 1 0 0 0 and 7 is represented as 0 1 1. And if you do bitwise and of it, if someone says that you have to do bitwise and of 8 and 7, so how it will done is, it will be done bit by bit. Like if this is the first bit, if this is the 0th bit, then 8th 0th bit will, like this and will be taken. 0 and 1 becomes 0. 0 and 1 becomes 0. 0 and 1 becomes 0. 1 0 becomes 0. So 8 and 7, the and becomes 0 and becomes 0. Okay, and becomes 0. So in bitwise operator operation, you just do all the operations, be it be and or XOR. You do it bit by bit. Okay, if one is there, then 0 0 is there. So you will do it bit by bit. Okay, we'll do it bit by bit. Okay, but how does it relate to the solution? How does it relate to the solution? How is and useful? Okay, so if I say what we saw earlier is, for 8, for numbers like 8, okay, we will get we will get only one, we will get one at only one position. In the number of positions possible, in only one position I will get one. Suppose here I get one and all the other ones are 0. All the other positions are 0. So if I do the bitwise and, if I do the bitwise and with all the ones, okay, if I do the bitwise and of all these zeros with any number, be it be 0 or 1, be it be 0 or 1, then this result would be 0 only, would be 0 only. And what would not be 0? What would not be 0? Whose output is trivial? This position, because if this is 1, the output is gonna be 1. And if this is 0, the output is gonna be 0. Okay, so this position tells us about what the output is gonna be. Okay, so this was about this position. Okay, so what I can do is for this is what I can do is it for this is, if I have 1 at this position, okay, so if I and it with the number just preceding it, because if we see the binary of 1 is 0 0 0 1, 2 is 0 0 1 0, 3 is 0 0 0 0 1 1, 4 is 0 1 0 0, 5 is 0 1 0 1, 6 is 0 1 1 0. 7 is 0 1 1 1. 8 is 1 0 0 0. So if you carefully observe the powers of 2, the powers of 2, suppose I put 2 raised to power 1, okay, 2 raised to power 1. So at this position, if I do the AND with the number preceding it, okay, I could get 0 at all the positions, 0 at all the positions, because if this is if this position is 2 raised to power 0, this is 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, okay. So if I do the and of these both, if I do the and of these both, I'll surely get 0, because as you can see, the number gets filled from the left hand side of the left from the sorry from the right hand side. Okay, so first this digit becomes full, then this, then both of this, then this, then this, then this, then this, then this, then this. Okay, so if you observe, this digit would be formed only when the other digits except this digit will be full. Okay, because if 7 can be represented, it can be represented as 111. Now these three bits this is the highest value, that it can have. So if I want to have 8, then I have to increase one more bit, okay. So my 8 would be like 1000, because these three bits were full, so I will follow a new chapter. And what I'll do is I'll just reverse this bit to 1, and all the other bits become 0. So if I do the AND with this, so as this position will always be 0, and in this, like in 1000, this is 8 and this is 7. So if, because these bits are full in this, these bits are full in this, okay, so this one would be 0 in this case, because this bit is not existing before the number, like in it is only introduced in the eighth number. So this bit would be 0, and in eighth number all of these are 0. So if I try to do the AND with these numbers, the solution becomes as 0 0 0 0, okay. And if you say that if I do with any other number, suppose that is not a power of 2, suppose I try to do it with 15. 15 is written as 1111, okay. So if I try to do it with 14, okay, so 14 is written as 8421, okay. 1110, 1110. So this would result as 10 becomes 0, 11 would become 0, 11 would become 1, 11 would become 1, 11 would become 1. So in this case, the number is not equal to 0. Whereas if you carefully observe all the powers of 2, all the powers of 2, may it be 16. If I try for 16, 16 is basically 10000, and 15 is, as we just saw, 0111. So this case would be having complementary zeros and ones. So if I can make the complementary zeros and ones, this would become 0. So this has become a identification mark of all those elements that are a power of 2, that if I do n and n minus 1, if that turns out to be 0, then it means it is a power of 2, okay, it is a power of 2. But if I do n and n minus 1 not equal to 0, then it is not a power of 2. It is not a power of 2. Is not a power of 2, because we tried for 15, right? The elements were not complementary. As we just saw, 1 0 and 0 1 becomes 0. So if or 0 1 0 0 becomes 0. So if I can make these numbers complementary like this, so the overall number would be 0, and this can act as an identification mark. This can act as an identification mark. Okay, this is an identification mark. So if n and n minus 1 equal to 0, that means it is a power of true. 2, then return true, else return false. Else return false. Okay, I'll just try to code it. The code is very simple. Suppose if the number is 1, basically we are now testing the edge cases. If the number is 1, okay, if the number is 1, it is like 0 0 0 1 and 0 0 0 0, so it would also become 0. Okay, if the number is minus 15, minus 16, okay, minus 16, so what would be the binary representation? What would be the binary representation? Okay, we will just for any negative number, as you can see, 2 raised to power x is equal to minus 16. This says that 2 raised to power x is minus 16. No matter any value put, if you put x as any value, this value is not gonna come. So minus 16 cannot be formed by any 2 raised to power x value. Okay, so if any negative value comes, you just have to return false. Just have to return false. Okay, so if there is any number that is equal to 0 or less than 0, then return false, else return not of and n minus 1. Okay, and I'll try to submit it. Now you will ask, while you have written this not, because if we see that the bitwise and of 8 and 7 becomes as 0 0 0 0. If I simply return it, then my answer would be false, because 0 acts as false and any other value acts as positive or true. Okay, so if 0 is there, I'll just complement it and return, so the answer would be returned as true. That's why I had written this answer. So okay, these two lines of code were like, the question was easy, but if you don't know how to manipulate the bits, how to have fun with the bits, then you can't solve this question. So for these two line of question, we have made this videos like this. I hope I have cleared all your doubts. I have not used the follow-up was, can you solve it without loops or recursion? I haven't used any loop. I just have used pure logic. Okay, so this was my solution. I had first explained you about what is bit manipulation. I had broken down the words. Now I have told you the optimal solution to this problem. Okay, I hope you guys enjoyed it. If you have any doubts, you can just comment it down in the comment section. And if you do like the solution, do share, subscribe, and like the video. Okay, thank you. Have a nice day. Bye bye.